So on 13, I do not have to know what the curves look like. I start the same way though. It says the area of the region enclosed. So they did use a different word. Instead of saying between, it says enclosed by these two graphs. So I don't pay attention to what they look like at all. I just do what I did on the last problem. I say, I need to find out how they interact. So I set them equal. I remember that it's a quadratic. So I move everything to one side. And then I factor. It's a difference of squares. So now I know the two x coordinates where the graphs intersect are x equal 2 and x equal -2. Questions? Okay. I know that this is a horizontal line, but I want to make the point I've been trying to make to Ava, which is I want to pretend I don't, because it really doesn't matter. If I have two curves and they intersect in two places, and I'm supposed to find the area enclosed by the curves, for all I care, one curve, I don't even look at the board. Like I'm not looking to make a point of how important it is to draw this very accurately. Here's one curve, here's the other. Perfect. Okay? And I'm a very efficient person, having worked as an engineer for 15 years. So I'm like, why draw a different graph when I can draw the exact same graph on every single problem and it always works? So this is what I always draw. I know that that's math heresy, but whatever. So, question? Cool. I need to find this area, the area between the two curves. I do need to know which curve is on top. Easy to find out. I pick the easiest x coordinate that is between, like not the one in the middle, but just what's easiest. What's the easiest x coordinate to use between these x coordinates? 0. Well, at x equals 0, this graph has a point at 0, 5. At x equals 0, where does this graph have a point? 1. So which graph is on top? This one here. So now I'm ready to go. So I need the integral from -2 to 2. Top function is y equal 5. Bottom function is x squared plus 1. I deliberately made 2 mistakes. You can raise your hand, talk to each other, tell me the 2 mistakes. I'll pay you 2 points. Feel free to talk. I'd like to have more hands. The mistakes are small, but they will cost you. You'll end up missing the problem. It's an FRQ, you lose points for bad notation. Julia, what are the mistakes?
There should be parentheses around x.
And there's another mistake. Do you see that?
And then shouldn't there be another parentheses around 5 minus x plus 1?
Yes. So I didn't. Anyway, you're right. Look, you have to have parentheses here and here. Because remember, this must multiply by this. And then because I subtracted 2 terms, I've got to have a set here and here. So how many knew it? 2 points. Okay. Question? 3 for Julia. Back to Keegan's question. I put this one in the medium category. Like there's a bit of work to be done, so it's not easy. I've seen problems that are much easier. But not too bad, because they didn't really have to know what the graphs look like. Fell out pretty fast. So here we go. I would clean up. So distribute the negative. So this will become 4 subtract x squared. And you just keep going down your page. I'm running out of page, so I make a copy and start back at the top of the board here. So we can get rid of all this for a minute. So again, like we were talking a moment ago, 2 items adding, I can take the antiderivative separately. So this becomes 4x, subtract x squared over 2, x cubed over 3, sorry. And then bar negative 2 to 2. Questions? I'm going to ask you a series of questions. I'll keep giving you points and then you'll see it. This line to this line is here, fundamental theorem. So how is little f related to capital? Perfect. So what's the derivative of 4x? 4. So what's the antiderivative of 4? 4x. Is that your question? 3 points. Yeah, John.
Like I get how everything works, but I'm just wondering how is the area that like the antiderivative, like how does that like actually work?
Really good question. Time for a ticket. That's a good question. That is
Nice,
really-
Charlie.
What a voice. Like a line from the Little Mermaid. What a voice. Look, the thing to remember is back here, like when I change screens, we kind of forget that we're finding area, to be honest. We just have an integral that needs to be calculated, and we just forget the story and just do the math. The story is better shown here. When they say find the area, they don't really mean find the area. What they really mean is find the area of 1,000,000 rectangles that fit within the space. So I'm going to draw one rectangle right here. We talked about in the last unit, to find the area of that very thin rectangle, I need the length times the width. dx is the width, and the length can be calculated by taking the y-coordinate at the top, which is 5, and subtracting the y-coordinate at the bottom, which is computed using this. You with me? So, right here, this is the length of a rectangle. Points for the whole room. Come on. Again, you should never just listen passively. Raise your hand and tell me. If this is the formula for finding the length of this green rectangle, what is the purpose of the x within the formula? Perfect.
Tell you which rectangle to find the right?
Perfect. Because there's 1,000,000 rectangles in here. Each rectangle is at a different x coordinate. This x tells me which rectangle. So I find the length, and then multiply by the width, and I do it for all these different x's. So on my calculator, that makes sense. Get it? If I can't use a calculator, we have to use this theorem here, the fundamental theorem of calculus, and we make a jump that to me is not intuitive at all. Like I can't see why this does the same thing. It does, but I can't, I'd have to sit and think about how to give you an explanation for it. It's not an easy explanation. It's like the theorem works, I know it does, the theorem makes sense to me, but why this is calculating area is kind of lost now. Like it got lost in the math. And that is not a good answer, but that's the best I can do right now.
Okay.
So I do think it's important that you feel comfortable as to why this calculates area. And then you say, oh, fundamental theorem is a bit of magic that allows me to calculate this without a calculator. Not a very good answer, but is that okay for now? Okay. Anybody else? So I don't ever expect anyone to, like what I expect is to hear, you're like, okay, it makes sense, I understand that I'm finding area. Then you say, I don't care about that anymore, I just want to find the integral. how do we find the integral? Fundamental theorem. So it becomes a problem without a story. So
Is it just because we're in a calc class that we know that this area differentiates from like normal area?
keep talking. I'm not sure what you mean.
Well, like, just like in other classes when we find the area, it's just like when they told us to find the area, it was so much different than this class. Is it just because we weren't in a calc class that they're asking this?
Good question. The shape that this actually looks like I can cheat, I know kind of what this all looks like. It's going to be this. Okay? So we're finding this area here. What's different, story from my life. My daughter was a senior in high school. She's taking calculus at a different school. So she just asked me for a little help. She's working on this kind of problem, right? And she's thinking exactly what you're thinking. You know, how do I find this area? Her little brother at the time was about 3rd grade. He's kind of sitting at the table and he's listening. And he gets all excited because he's learned about area. And he's like, oh, I can help. I'm like, okay, Derek, tell us how to help. And he's like, area is really easy. He picks up some paper and he draws a little picture. And he goes, look, a little 3rd grader, right? He's like, if you're trying to find this area, you just draw little squares. Count them up. That's the area. Agreed? Then I said, awesome. Here's her sister. His sister's name is Jamie. I said, here's Jamie's problem. She's trying to find this area. And it has this curve. What do? It's real quiet, right? He's thinking. A few seconds go by and he goes, you don't. Here's the difference. In previous classes, you typically are finding the area of nice rectangular shapes, or shapes that can be kind of broken into rectangular shapes. It's pretty much all related to rectangles. And so you didn't need calculus to find the area. You could do it geometrically. The moment we introduce strange curves, there is no way to find the area without calculus.
What about like the area of a semicircle?
I don't have time right now, but I can show you how to use calculus to find that area. And I'd have to trace back and see if they, that's a good question. I don't know the history on that one.
Isn't it like, is the area for circles like higher square?
Higher squared, yeah. I don't know the history, because that came before calculus, for sure.
Yeah.
But I don't know the history of how they figured that out. But when we got to complex curves, not a simple semicircle, yeah, calculus was required. And so the approach is different. Instead of remembering a formula, we don't. We say we're going to find the area of a rectangle and then fill the space with rectangles. Does that answer your question? Yeah. 3 points. There you go. Awesome. So back to here. Now we're just going to, as I've heard people say, math it. Plug in the 2. Please make sure you put parentheses every time you replace an X. It will save you.
Can they grade every single thing you write down?
I believe strongly that if you write a statement and you put equal and it's not equal, you will lose points. I believe strongly that if you forget to put equal, you also lose points. Because the grader can't grade a pile of numbers. After that, it's more like, in many problems, there are no required elements. So as long as they can follow your work, you're fine. In a few problems, there are required elements. We practiced that on the last test. And if you forget those required elements, you do lose points. Again, because we spend March and April practicing, hasn't been a problem. Like, that's not why, it really just doesn't get in the way. Like, you learn enough to write, you're fine. So. Okay, look up. Really important here. As soon as I put that minus, I have to remember, I'm now going to write 2 more terms. So I've got to have parentheses. Without the parentheses, I will make a mistake. Question? Cool. So now we plug it in. Make sure you put parentheses every time you take away an x. Now, back to Meredith's question. On the FRQ section, you now stop. Please don't go any farther. Like, just stop there. Multiple choice, I gotta find the answer, so I have to keep going. Look over here, everybody, look. Julia, look up for just a second. This is a huge hint, and it didn't occur to me for years. Like, whenever I would work these problems, I would waste a lot of time combining these two, because this is going to be a fraction, this isn't, and I'd spend the time, common denominator, all that stuff, okay? Don't. When you're working an integral, these two terms are coming from this formula. These two terms are coming from the exact same formula. So get them all written out first, and it's a lot easier. Don't spend time trying to combine these. So this becomes 8 minus 8/3. This is negative 8 times that will be positive 8. This would be negative 8/3, positive 8/3, back to negative 8/3. So negative cubed is negative. That negative switches it to positive. Distributing that negative switches back to negative. And so what I do now is, instead of trying to combine these two, it's much better to combine these two and these two. Just saves some time. So now you have 16. Subtract 16/3. Now you do have to do the common denominator thing. So I have 48/3. Subtract 16/3. 32/3. Can someone confirm the answer? Thank you. Thank you. Question. I'm just like all of you. I make mistakes too, so I just want to make sure. Anybody else? Cool. Next one.